Good evening, everyone. Tonight's speaker is Dr. Christopher Glean, a geochemist who works at the Southwest Research Institute in San Antonio, Texas. His research centers on the formation, evolution, and habitability of icy ocean worlds in our outer solar system. In projects with NASA, he studies spacecraft data from planetary missions in his quest to see if life may be hiding in other places in our solar system. Please, everyone, welcome Dr. Glean.
Hello, everyone. Thank you, John, for the introductions. I'll get started by sharing my screen, and then we'll get the show on the road. Okay, do you see my slide okay?
You do.
All right, great. Yes, I was saying thank you so much, John. I really appreciate the invitation, and I'm delighted to see everyone in the audience who's interested in learning about some of our new results in the solar system. I got to warn you that I'm a geochemist, so what that means is I use like concepts of chemistry to understand chemical observations of other planets or moons or objects in space. So you're going to get a nice wallop of chemistry. So buckle up if you're not prepared for chemistry, because we're going to hear a lot about it. And with this talk, you'll see here's two objects, Eris and MakeMake, I'll be discussing. And this is a presentation. It's kind of like an adventure that I've been taking for the past year and a half. So I'm excited to share this with you. These are research results that we published about 6 months ago. And before about a year and a half ago, I actually didn't know much about Eris and MakeMake. I'm a professional planetary scientist, but as John mentioned, a lot of my research is actually focused on the moons of the giant planets. So if you're interested in that part of my work, you can try searching on Google. I study bodies like Titan and Europa and Enceladus. But today we're going to be talking about worlds way out there. I'll go to the next slide here. So you probably have heard about the different zones of our solar system. So the zone that we live in is known as the inner solar system, and that's where the rocky planets live. That's Mercury, Venus, Earth, and Mars. It's very close to the sun, so the surfaces are relatively warm. Then as you move further out, we enter what's known as the outer solar system, which includes the giant planets region. So that's a region between the orbits of Jupiter, Saturn, Uranus, and Neptune.
Chris, excuse
And then,
me.
yes.
Yes. We have a vehicle that needs to be moved. I apologize for the interruption.
BMW gray, license plate Lima 86.
Yeah, I got
Like
it.
a Charlie.
Cool. You got it.
Thank you.
All right, thank you very much.
Sorry.
Thank you.
Didn't know.
All right, Chris, please continue. Thank you. Sorry for the interruption.
Oh, no problem. I'm glad somebody's car's not going to get towed. So yeah, what I was saying is the second zone is the giant planets, and we've sent spacecraft that have orbited some of the giant planets and have zoomed past some of the other giant planets. So we've learned about the giant planets and the moons that orbit them and their rings, and it's been great science. But then over the past 20 or 30 years, we've learned that there's this whole other third zone that's really vast out past the orbit of Neptune. And it's called the Kuiper Belt. And we first knew about it when we discovered Pluto about 100 years ago, not quite 100 years ago yet. And it was thought to be the 9th planet, but it actually turned out to be the first resident that we discovered of this vast arena known as the Kuiper Belt. And that's where Eris and MakeMake live. Just a little bit about everyone's favorite KBO, because this kind of can set the tone for what we might expect in the Kuiper Belt. The Kuiper Belt is incredibly cold. So even the surface of Pluto, it's kind of in the inner Kuiper Belt. The surface of Pluto is way below the temperature of liquid nitrogen. So it's incredibly cold. And you might think that these are just frozen ice boxes that are orbiting the sun. But when we flew a spacecraft past Pluto 9 years ago now, we discovered that these icy bodies can be surprisingly diverse, complex, and even active. So here's just a few highlights from Pluto. You can see in the bottom image shown here, this white feature, we call it Pluto's heart, right? It's actually known to be a vast ice sheet that's made not of frozen water like, Antarctica or Greenland, but it's actually frozen nitrogen ice. So it's N2, it's like the nitrogen, the same kind of molecules in our atmosphere. When it's so cold, those actually freeze out and they form a vast sheet of ice that's about the size of the country of Pakistan, and it's a few miles deep. And then another feature I like to point out are these other features on the far right-hand side. These are known as ablated terrains. You see they're kind of like a little bit orange colored, and they have this interesting snakeskin texture on those. And those are actually now known to be made out of methane that has been sculpted through processes involving methane converting into a gas and then refreezing onto the surface again. It's formed these complex patterns on the surface. So let's talk a little bit more about Pluto's poorly understood cousin that live in the Kuiper Belt. So you can see on this image here, here's Pluto and its moon Charon. And these are just a handful of objects. These are the biggest objects. There's many other small objects that reside in the Kuiper Belt. But out of the big ones you can see here, these are roughly 2-scale images. We have Eris, Haumea, MakeMake, Gonggong, Quaoar, Sedna, Orcus, and so on. And these bodies, they're roughly, kind of like Pluto size. They're a little bit smaller than Pluto. So they're fairly large objects in the solar system. They'd be comparable to like a middle-sized moon of Saturn, for example. Eris, as you might surmise from looking at this image, it's the biggest body that's been discovered out past Pluto so far. People are looking for the elusive planet 9. You may have heard of that. But so far, as we know, Eris is the biggest body out past Pluto. It's very far from the sun. It can actually reach almost to 100 astronomical units. And so you guys are astronomers. 1 AU is the distance from the Earth to the sun. So when Eris is at its furthest point from the sun, known as aphelion, it's 95 times the distance it's 95 times the Earth-Sun distance out there. So it's incredibly far. That explains why it's so cold. And then this other body that we'll be discussing in some detail today, MakeMake, is similarly far from the sun. It doesn't go quite as far out as Pluto does, as Eris, but it goes further than Pluto. And you can see in this image here, it's kind of in between the size of Pluto and Pluto's moon called Charon. And we don't know much about these worlds. That's one of the reasons why they're really fascinating to me and a lot of other scientists, is we have yet to fly a spacecraft past any of these bodies. So we've never taken any pictures of them up close, and we don't know what they look like. So when you see these images in this graphic shown here, these are just artistic renditions. No one has a clue what the surfaces of these bodies really look like, or what is happening on these bodies. So that's one of the mysteries that we're going to start to try to crack throughout this talk. And our tool for cracking the mysteries of Eris and MakeMake is the James Webb Space Telescope. If you haven't heard about James Webb, it's the latest and greatest observatory that's been launched into space by NASA. So the predecessor of James Webb, you can think of as the Hubble Space Telescope, and that's been operating for a few decades now. We just launched the James Webb Space Telescope, so it's been in development for a long time. It started in the mid-1990s. So I wasn't even graduated from high school when they first started this mission. That's how long it's been. And then it finally launched just a couple of years ago. Hopefully some of you had the chance to watch that launch on TV. And there was a brief period of commissioning after that, and it really started to stretch its sea legs, or space legs, I guess, in July of 2022. So it's been about 2 years now since James Webb has been observing the cosmos. And it's an incredible workhorse. It's been observing the universe, so we've been getting information about molecular clouds, you know, the birthplace of stars, looking back in time to some of the first stars and galaxies, looking at exoplanets. So James Webb is able to collect light from distant exoplanets, and we're learning about their atmospheres and what kind of molecules are present. And that's helping to guide the search for life on other planets. But also, people like me, we're using the James Webb Space Telescope not to peer light years into space, but just look into our backyard, into the solar system, and be able to look at the solar system in a new way. And we looked at Eris and MakeMake near the beginning of James Webb's operation. So Eris was observed in August of 2022. So about a month after science operations kicked off, then Eris was already scheduled to be observed. So that kind of shows you that Eris is thought to be a very important object for planetary astronomers. And then we followed that up with MakeMake not that long after. A few months later, we observed MakeMake. And both of these observations are really good ones. So you can see here, I wrote down, we had about 40 minutes and 54 minutes of exposure time. And that's really good because James Webb is extremely valuable. Lots of people want to use it to observe everything in the cosmos. So to be able to use this resource for almost an hour a piece on these bodies is great. And we got a great set of data that I'm going to show you pretty soon. Here's what James Webb saw sort of from the zoomed out point of view. On the left-hand side here, here's Eris, and the right-hand side, here's MakeMake. So hopefully this doesn't look disappointing because I told you James Webb is super powerful, but we can't zoom in and see, let's say, an ice volcano on the surface of Eris with James Webb. These bodies are still very far away. So even with the greatest technology that we have available currently, a lot of these distant objects still look like a collection of pixels. So you can see, you know, Eris is just a handful of pixels here, and MakeMake is roughly the same. Here's what Hubble Space Telescope saw about 20 years ago, 10 to 20 years ago, what Hubble saw. So not too different, right? They're not really, they're not dots or points of light. They look like discs, but you can't really see a lot. You can kind of see here's Eris and its moon Dysnomia, and then here's MakeMake, and its moon has not been named yet. But where James Webb is extremely powerful is the type of light that it's able to see. And so sunlight, if those of you who haven't heard about this before, sunlight is known as white light. So it looks white to us or kind of yellowish. But if you pass sunlight through a prism, you can actually separate it into its different component wavelengths, and you get a whole continuum of different wavelengths spanning ultraviolet light. So this is the kind of light that will give you a sunburn. We see visible light, and the Hubble Space Telescope was able to look at visible and ultraviolet light. What James Webb allows us to do is look at longer wavelengths into the infrared light. So this is past the red in the spectrum. And that, it turns out, is a hard part of the spectrum to look at because we have much bigger telescopes on the ground, on the surface of the Earth. The problem if you use a ground-based telescope is you have to look through Earth's atmosphere, and Earth's atmosphere has molecules, right? There's gas molecules in Earth's atmosphere, and they actually block out a lot of the infrared light that you'd want to see to learn about the surfaces of these distant Kuiper Belt objects. So for the longest time, we were almost blind in the infrared. We had not been able to see much at all. So astronomers, myself included, were keenly looking forward to what James Webb would reveal to us. I'm going to tell you a little bit about chemistry to kind of set the stage for why this all works. So you can kind of think of molecules we know that they're composed of chemical bonds. So it's how atoms are glued together. And you can think of chemical bonds in a simple sense as like little springs that hold the atoms together. And these springs will vibrate with different frequencies depending on how strong the chemical bond is. And if you have a molecule, let's say, then you have collections of chemical bonds. So in this case, I'm showing you methane. CH4 has 1 carbon atom and 4 hydrogen atoms bonded to it. And if you have multiple chemical bonds like that, then you can have what are known as modes. And this is like the different combinations of how the bonds can vibrate. So a simple mode would be what's called a symmetric stretch, when all the bonds are kind of pulling apart from one another. And then those of us who do spectroscopy, we refer to that as nu1. And then you can have different combinations involving some bonds kind of like wagging, or other bonds, some of them stretching and some of them compressing. And those give you other modes. And it turns out that nature has done us a fabulous favor by having chemical bonds with these different modes, because they absorb light in the infrared part of the spectrum. And when they do that, they create what are known as bands. And bands are super powerful because as astronomers, we can collect the light that's separated through a prism, and then we can look for these bands. And those bands are like fingerprints from a molecule. So if we can detect these bands in the infrared spectrum, then we can diagnose and infer what kinds of molecules are present, even on a body as distant as those in the Kuiper Belt. And this is what we saw when we collected the light from Eris. This is the latest research that we have on this topic. And so you could see a body that is perfectly reflective would have an albedo. That's roughly the reflectivity of 1. So when you have these dips here, that means you have some kind of molecule on the surface that's absorbing the light. And I've done us a favor by just copying and pasting one of those modes of methane on this figure shown here. So we can associate this mode of methane with this deep absorption band that is detected by James Webb. So from that relationship, then we can identify frozen methane on the surface of Eris and MakeMake. So methane, for those of you who don't think too much about these bodies much, methane is natural gas. So if you ever use gas, like let's say to heat your home as a source of energy, we burn natural gas to produce heat and heat our houses. On the surface of Eris, what the spectrum is showing us is that methane molecules are present, but because the surface is so cold, the methane is not methane gas, but it's actually frozen out on the surface as an ice or a frost. And that's what the data are showing us from the James Webb Space Telescope. And you might also notice there is a lot of methane on the surface of Eris. So I mentioned, if it's perfectly reflective, it'd be around 1. These are very deep absorption bands. So there's a lot of methane ice on the surface. Oops. If any of you want to quickly scan this and you're interested in learning more about these data, there's a paper that was published by Will Grundy, and you can learn a lot more details into the technical aspects of this work. All right, so here's the really exciting stuff, is we detected some new features at longer wavelengths. And these are the wavelengths that are unable to pass through the Earth's atmosphere. So this is our first look at this part of the spectrum that we've ever seen on Eris. And it turns out we've learned a lot from looking at these data. I just want to point out a couple of notable discoveries we've made. We detected the presence of N2. So this is nitrogen. It's the same nitrogen that we breathe in our atmosphere. But on the surface of Eris, what we're finding is this absorption feature from N2 that is due to nitrogen ice. So again, because it's really cold, the nitrogen molecules are frozen on the surface. And the other thing, we didn't see any carbon monoxide, which is kind of interesting from the point of view of planetary scientists, but it just means that Eris and MakeMake don't look much like comets. They look like something else. And the other thing that's very obvious in the spectrum are these dips that you can see here, and we've labeled them CH3D. This is known as deuterated methane, and it is central to the story that I'm about to tell you. It's the first detection, in fact, of CH3D on any of these bodies in the Kuiper Belt. So you might be wondering, if case you're a little rusty on your chemistry, what is CH3D and deuterium, and why is this important? So CH3, what chemists call this is it's an isotopolog of methane. So you can think of it in normal language as like another form of methane. And it has the same atoms as normal methane. So you have a carbon atom and you have 4 different hydrogen atoms. That's what makes it methane. But in CH3D, one of the hydrogen atoms has been replaced by a special isotope, and we give this isotope the name deuterium. What an isotope is it's a form of a chemical element that has the same number of protons as other atoms of that element, but it has a different number of neutrons. So for those of you who aren't familiar with atoms, we think all matter is made out of atoms. And at the center of an atom is known as a nucleus that contains protons and neutrons. Proton that determines what chemical element you're dealing with. And then the neutrons is another particle that has a neutral charge that gives the nucleus extra mass. So the normal form of hydrogen has 1 proton and 1 neutron, just 1 proton and 0 neutrons in a normal hydrogen atom, and has 1 electron. For deuterium, it has 1 proton and 1 neutron. So that's the key difference, is having that extra neutron. And what it does is it increases the mass of a hydrogen atom from a mass of 1 on our normal atomic scale to a mass of 2. And it was discovered in the 1930s. So really, deuterium is a key figure in the dawning of the atomic age, when chemists and physicists cracked apart atoms and we learned about the structure of atoms. And deuterium was a key figure in that story. It's important in geochemistry and cosmochemistry because we've learned from observing different primitive bodies or other solar systems, molecular clouds, and so forth, that different planetary building blocks actually contain different concentrations of deuterium. And I heard that you all are going to be studying or having access to a meteorite sometime soon. So that's extremely relevant to this, because this is an example shown here. This is known as a carbonaceous chondrite. It's a type of meteorite that's very rich in carbon. And this is one of the most famous ones. It's called the Orge carbonaceous chondrite. It's loaded with carbon, and it's also loaded with water and some other building blocks of planets. And it turns out if you dissect this kind of meteorite, it turns out that different carriers of hydrogen atoms have different concentrations of deuterium. So deuterium can be used as a tracer of the sources of hydrogen atoms that get delivered to planets. And how we do this is we quantify the amount of deuterium by what's known as the D to H ratio. So it's the deuterium divided by hydrogen ratio. So you just take the number of deuterium atoms, divide that by the number of normal hydrogen atoms. Deuterium is very rare. So it's fantastic that we detected it on Eris and MakeMake because it's kind of hard to find. Here's an example. So if you take a cup of seawater and you analyze for the different elements in seawater, for every 10,000 hydrogen atoms that you scan through, about 1 to 2 of those, you'll have 1 to 2 deuterium atoms for every 10,000 hydrogen atoms. Not much at all. So it's almost like a needle in a haystack, right? So to be able to detect deuterium on the surface of Kuiper Belt objects is really incredible. I think I already mentioned, so it's an excellent tracer for where stuff came from. Like we like to know how a molecule got to a planet, or what's happened to the molecules that we see on the surface of a planet. It's like a detective story to figure out, what happened in the past. And on Earth, we've used these kinds of measurements to understand the origin of water. That's a really critical part of Earth's story. And so chemists and geochemists have used measurements of the D to H ratio to learn about the history of water on Earth. And so a natural question then is to ask ourselves, now that we have this kind of tool and this new measurement for other places in the solar system, can we use it to learn something about the origin of those molecules? So let's go back to the spectrum again. And the striking thing is all this methane, right? So where did the methane come from? And now with the James Webb Space Telescope and our ability to understand the deuterium to hydrogen ratio, we can start to piece together what this all means. So what people have done is they've made laboratory measurements of methane ice. So you could try to simulate the surface of Eris and MakeMake in the laboratory, where you take methane gas, you freeze it out at very low temperatures, and then you collect spectra like the spectra that James Webb Space Telescope collects. And then you can see that different features shown in red are produced when you have deuterium in the methane molecules. So what the team did, this is already a while ago, this is in preparation for James Webb, but they made these laboratory ices that were meant to simulate Eris and MakeMake, and we figured out how big of a dip you get for different D to H ratios. So, if you have lots of deuterium, then you get a huge dip shown here. And then if you just have a small amount of deuterium, then you get a small dip, right? So we're able to do these laboratory measurements, and then we use the laboratory measurements to find the D to H ratio that best matches what we measured on the surface of Eris and MakeMake. And what we came up with when you do all that analysis is we derived a D to H ratio of about 2 to 4 times 10 to the minus 4. So it's about 300 parts per million. There's a little more deuterium than in Earth's seawater, about double, but it's still very rare on the surfaces of Eris and MakeMake. So the question that we then asked ourselves is, we got this number, what does this number mean? And this is where I did a lot of work here, is we try to come up with this framework to assess different sources of methane. And these sources, we call them primordial, abiotic, and thermogenic. And I can explain what these all mean. So a primordial source of methane means the methane you see on Eris and MakeMake, that methane was delivered as methane molecules. And the way that you can get methane delivered as methane is if you have comets or things like comets that have delivered methane to the surfaces of these bodies. So this is one example. This is comet Hale-Bopp that was studied in the 1990s. It was an incredibly bright comet. And from measurements of comets like this, we learned that comets contain methane. So this is one possibility to get methane on the surface of a Kuiper Belt object. And there's other possibilities. So this other source, known as abiotic, people who study the Earth are familiar with this. we find methane when we send submarines to the bottom of the ocean. So you can go to certain spots on the bottom of the oceans, and there are volcanoes erupting at the bottom of the ocean. And this is just one example. They produce these black smokers where superheated water is erupting at the seafloor. It produces this black smoke. And if you sample this stuff in a submarine, you find that it's loaded with methane molecules. So processes associated with high temperatures and heating carbon in contact with rocks can produce abundant methane. And then the third source of methane that we'll be studying is known as thermogenic. And this is the kind that goes back to my comment about heating your home. We mine natural gas and oil, and we use that methane to heat our houses, right? And it turns out that methane actually comes from dead stuff. When you have dead microbes and other organisms buried under material on the seafloor, that stuff eventually gets heated up inside the earth, and that carbon-rich material transforms to produce the oil that we use to run our cars, and it produces the methane that we use to heat our houses. So that's another way that planets can make methane, is when you have carbon-rich organic materials being heated. What applies to Eris and MakeMake? Prior to the D to H measurement, we couldn't answer this question. It'd be in the realm of speculation. But now that we have this measurement, we can start to do science to start to try to eliminate possibilities and get closer to the answer. And so what I did, I'm a geochemist, I made different models. And the idea is we consider those three sources: primordial, abiotic, and thermogenic. And we make models to predict what we'd expect to see for the D to H ratio if the methane on Eris and MakeMake was primordial, abiotic, or thermogenic. So I scoured all the information that's available, looking at meteorites or comets, hydrothermal events, and we made models to make predictions. And here's how the model works. You use something known as a fractionation factor. We call that alpha. And we obtain values for these fractionation factors by looking at the places where methane is produced on Earth or elsewhere in the solar system. So when you're thinking about a hydrothermal system, for abiotic methane, we look at measurements of hydrothermal systems. And from those measurements, then we're able to determine the value of alpha. And the other critical ingredient of this calculation is the D to H ratio of water, because it turns out if you make methane in a hydrothermal system, there's a lot of hot water that mixes with the methane. And so to get some information about that quantity, we looked at the ranges of D to H measurements in comets. And so if you have those two pieces of information, you can multiply alpha times the D to H ratio of water to then predict the D to H ratio of methane. That's what we did. And then this just shows you some more details. So you got to kind of, I won't go through this in gory detail, but you got to kind of think through the whole process of forming the planet and how the planet evolves to make these kinds of predictions. So you got to kind of start with the building blocks and think about if you might have any volcanism or other types of hydrothermal activity, or if processes at the surface of the body might lead to changes in these measurements. So it requires, it's a huge thought exercise, and you got to try to constrain all of the different unknown parameters to get to the end of the calculation. If you do all that, you can make this kind of prediction here. This is the plot that I made. So what this plot is showing you, this is the predicted deuterium to hydrogen ratio of methane as a function of the D to H ratio of water. And then here's our different options, right? The primordial, thermogenic, and abiotic, they all got ranges because we can't say the D to H ratio will be one specific value because there's just too many things we don't know. So there's going to be some range of uncertainty. But what's interesting is if you piece all of the information that we have available together, this box leads to our best estimates from all that information. And using the information contained in this box, then we can translate that into specific ranges, which is shown here. This is just a simple bar chart. These are our hypotheses, the primordial, abiotic, and thermogenic methane. And they have these different ranges. So now the critical question is, how does this compare to Eris and MakeMake? That's how it compares. And you can immediately start to draw some very interesting conclusions, I think. So one conclusion you might notice is that the D to H ratio of primordial methane is predicted to be too high. You know, even at its lowest point here, it's above these bars here, right? And then these other options, the abiotic and thermogenic, they actually overlap with the measurements. So as scientists, we say that those are consistent with the data. And this was very interesting for planetary scientists because I mentioned these are cold bodies, and a lot of scientists had this expectation that the cold Kuiper Belt objects would be like supersize or giant comets. So, you know, you can imagine you just take a comet and you supersize it, and you just kind of have frozen worlds out there that are in a state of deep freeze. And for that kind of scenario, you would predict these bodies to have primordial methane. And that appears not to be the case. So something interesting and unexpected is happening here. And we ask ourselves, well, what does the presence of abiotic or thermogenic methane mean for the origin and evolution of Eris and MakeMake, this unexpected sources of methane? It means, if you remember, I told you what abiotic and thermogenic methane are. You got to cook those forms of methane up. You got, for the abiotic source, you got to cook the methane and make it in the presence of hot rocks. Or if you have thermogenic methane, you got to cook up organic material to make the methane. So you need warm temperatures, and this directly flies in the face of that preconceived notion I had of these bodies being frozen ice cubes out there. It appears from these new data we got from James Webb that there's evidence for much, much higher temperatures than we find on the surfaces of these bodies. And what this means is we need this, we're inferring that this process known as radiogenic heating is occurring in the interiors of these Kuiper Belt objects. What is that? Radiogenic heating comes from radioactive decay. So you probably heard of radioactive materials, right? It's not good for you. It can give you cancer, you can die. It turns out that all natural rocks are actually radioactive. They're just radioactive to a very low degree, so we don't get cancer and die instantly. But they contain radioactive elements like potassium-40. So this is one isotope of potassium, and then isotopes of uranium and thorium. So these are heavy elements that are unstable, and they slowly decay with time. And by slow, I mean like really slow. So it takes like hundreds of millions to even 1 billion years for some of these isotopes to decay. But when they do decay, they release high energy particles like electrons, gamma rays, and alpha particles. And those particles can heat the rock. And this is just one example of a radioactive rock. Hopefully many of you are familiar with this. This is known as granite. So this is the kind of rock that composes Earth's crust. It's abundant. You've probably seen it on countertops. This particular type of granite, it's known as pink granite. It has a lot of this pink mineral here. This mineral is rich in potassium. So this is the radioactive mineral I was telling you about. Radiogenic heating and radioactive decay. This is a major source of energy inside rocky planetary bodies. So this is a cutaway of the Earth. We think the Earth's interior. So if you were to dig a deep hole into the Earth or take a trip into a mine several miles down, you would find that it gets uncomfortably warm down there. And that's because the Earth's interior is being heated by radioactive decay. That's one source of heating. And that heat is driving the churning of the Earth, which is responsible for the geological activity we find on the surface of the Earth. So this radiogenic heating is a really important process inside of rocky planets. And how this all relates to Eris and MakeMake is the surfaces of these bodies have frozen methane, right? But if they have warm temperatures deep down, that means they must have rock deep down that provides the heat source for this chemistry to make the methane. So this is just a simple artist cartoon showing what we think the interior of Eris and MakeMake look like, where we think that there's a big chunk of rock in the middle, and we call that the rocky core. And that's where the planetary body can build up heat that drives chemistry. And here's the scenarios that we think are suggested from our findings in cartoon form, mind you. We don't know exactly what's going on, so we proposed a range of 3 scenarios here. And at the bottom, I've talked a lot about rock so far. We think the rock is being heated by the decay of radioactive elements over long periods of time. And then that heat is driving some chemistry. We're not sure yet exactly the chemistry. It could be hydrothermal activity at the ocean floor. There could be an ocean that's circulating through hot rocks like we find on the Earth. Or maybe the rock is just slowly being baked out and the methane is escaping through this baking process and eventually being carried to the surface. So what's interesting, I think, about these kinds of ideas is they're hypotheses that we're now able to start discussing and thinking of new tests because we had this wonderful source of data provided by the James Webb Space Telescope. I know we're almost out of time, so just a quick couple questions we might have is, is it reasonable to think there could be hydrothermal systems in a Kuiper Belt object? About 20 years ago, not quite 20 years ago, there was some modeling studies where people first predicted that some of these Kuiper Belt objects like Eris and Pluto could actually have a rocky core that's covered by an ocean of liquid water. So that might set the stage for hydrothermal activity. And more recently, there's been other information where people have looked at the spins of Eris and its moon, Dysnomia, and they've concluded that to reach this state where their spins are perfectly in sync means that Eris has to have kind of like a squishy interior, which means that you have to have a rocky core separated from the ice and the water. So this seems to be pointing in the direction that is needed to support hydrothermal activity. And then there's been other work since then. So people have looked at Pluto. We think that Pluto now has an ocean. People have made models of Pluto's rocky core. So this is known as a thermal evolution model, where you can calculate the buildup of heat inside of the rock on a Pluto-sized body. And you could see if you have a big piece of rock, a big rocky core, you can reach hundreds of degrees in temperature going deep down into the rock. And here's just another case for a body that's not quite as big as Pluto or Eris, and more similar to the size of MakeMake. Similar models point to high temperatures being reached in their rocky cores. And so the last message I'm going to leave you with, I feel like being a little bit philosophical. I think of planets, we're always trying to say what planet is Earth-like or something like that, right? When we're looking for life on other planets. And how I like to think of planets is they're like individuals, kind of like people, where they have like they were born in a certain environment and they had like their whole life story. And we're trying to piece all that together. And it's kind of like this notion that I have of planetary psychology, where we're thinking about what is the role of nature versus nurture. And on a planet, you might think nature is like what the planet was born with. So in our models that I presented today, that would be like the primordial scenarios of methane that don't match the D to H ratio that James Webb was able to determine. Nurture is how the processes that have occurred on the planet through time have changed it and led to what we see today. So the conclusion from all of this is that when we're thinking about these large Pluto-sized worlds that inhabit the far reaches of the solar system, the evidence supports the role of nurture. The evolution of these bodies has been more critical than what they started with. And that's helping us to piece together the story of how our solar system has formed and evolved in this still very mysterious third realm of the solar system in the Kuiper Belt. And with that, I'll switch to my conclusion slide. You can read some of these conclusions, and I'm happy to take any questions.
Are there any questions from the audience here? There's got to be one or two, I'm sure. Yes.
Yeah, so I'm curious about how you determine what makes a good like stand-in for Eris or MakeMake. Like you mentioned Titania or Titan or whatever as a reasonable substitute. I'm curious what makes it a reasonable substitute.
It's a good question. The only kind of data we have from Eris and MakeMake are we have their sizes and we have their densities. So the density comes from combining the size and the mass. So we can scour around for other icy worlds in the outer solar system and try to find bodies that are roughly similar in size and density. And density is useful. I should have explained this earlier before I started answering this. Density is useful because it tells you how much rock is inside of the planetary body, because rock is dense. So if a body has a high density, that means there's more rock.
Thank
There
you.
was another question over here. Yes.
Yes, for similar exposures, how faint an object could this analysis be done for?
That's a good question. So we are looking at the data from some of the other bodies, like Sedna is further than Eris and MakeMake and Pluto. We've detected interesting ices on the surface of Sedna, but no evidence yet of methane or a D to H ratio. So we might be near the limit of what James Webb can tell us as far as this tracer of planetary history.
We still have a couple of questions here.
Yeah. Hey, from the amount of methane that's on the surface and how hot the core could potentially be, is that something that can lead to like a planet exploding?
I don't think anyone's modeled that, to be honest. You could build up pressures if you make methane, deep inside the rock. That could generate high pressures. But on the other side of the coin there, deep down into the cores of these bodies, the overlying material has a lot of pressure that can hold it in. So I think it'd be a great project for like a student or even a professional scientist to try to make some predictions of what kinds of pressures you might be dealing with. It'd be interesting because that might, if you built up high pressures, that might suggest a pathway for the methane to go from the interior to the surface.
Thank you.
I have a question. The methane found on Pluto isn't similar? You don't find the same conditions?
Pluto's interesting. So we detect methane on Pluto, as I mentioned, I think on the first, second or third slide.
Right.
What we don't know on Pluto yet is we don't have a measurement of this deuterium to hydrogen ratio. We have spectra from James Webb, but Pluto is actually harder to determine this isotope ratio because Pluto has a lot of complexity on its surface. It has lots of different ices and other types of materials. And it turns out when you have more things on the surface, when you look at the infrared spectrum, you start to get interferences. Like there's different absorptions start to overlap with each other. And it makes your life more difficult when you're trying to determine some of these isotopic ratios.
Let's see.
We're working on it, but I think we're going to be able to pull something off. But we started with Eris and MakeMake because they're easier. The surface compositions aren't so complex.
Mhm.
We still have a couple of questions here?
Yeah, I got one.
Yes, please.
Hey, this alien ocean at the bottom, in the middle of this exoplanet, like, how much of it could you actually speculate is like hydrogen and oxygen, like our ocean, rather than like hydraulic fluid or sedimentary sludge?
It'll probably be more like the second option. So our oceans are thoroughly oxygenated. So our oceans contain abundant dissolved oxygen gas, O2, that's used to support more complex life forms like, fish and dolphins and so forth. For the ocean, the ocean of Eris and MakeMake that we're inferring, that would be a deep, dark ocean. So you wouldn't have the availability of sunlight and photosynthesis to make oxygen. So it would probably resemble fluids that are found in anoxic environments like sedimentary pore fluid or something of that nature.
I think there was another question in the back. No? Yes, please. Yes.
Is there reason to believe the methane is being renewed, or could it be quite old?
We have a reason to believe that it's being renewed. We cannot argue, or the data do not allow us to make a conclusion one way or another, whether there could be current activity that's renewing the methane. But there's two important findings. One finding, and this is before James Webb, is Eris and MakeMake have very high albedos. They're reflective. And so what that means is we think that a lot of bodies in the outer solar system, they gradually weather when they're exposed to cosmic rays and small bits of dust out there. They get coated and they darken over time. And Eris and MakeMake, especially Eris, are very reflective and bright. So that would suggest that there's been geologically recent outgassing. And then another reason also is methane is gradually converted into more complex organic materials. If you expose methane to cosmic rays over millions to billions of years, that methane will gradually undergo chemical reactions when it's exposed to the harsh radiation of space, and it forms like this tarry reddish material, and that also will tend to darken the surface. And so the fact that we're seeing bright surfaces and we see abundant methane suggests that the methane has probably been delivered geologically recently, but we're unable to say, is there a cryovolcano that is erupting right now, or could it have erupted 50 million years ago? That's going to require ongoing work. And if you read my very last point down here, I think we're probably going to need to eventually send a space mission to try to answer those kinds of questions, because there's only so far you can take the evidence from remote observations. Even with James Webb, you cannot see the surface. But if you were able to see an ice volcano erupting or some other features on the surface, that could go a long way towards answering this kind of question.
I have
Yes,
a
please.
very basic question. Where did
Sure.
where did the name Maki Maki come from?
Yeah, I don't know that too well. I think so. It was discovered about 20 years ago, and I think it's named after some traditional native naming in the Americas, but I could be mistaken. It's a very fun name, though.
It is.
It does. Sounds cool.
Yeah, my kids love it, so it could be a good name to get kids excited about space, because you have Pluto and then you have Maki Maki. So
All right, any other questions here? I don't, yes, please.
How do you know how far away the planet is if you've never sent a spacecraft there?
Good question.
how far away it is? I think the way that people do that is they map out the orbit of the planet. So you can track Eris and MakeMake in the night sky, and because it's orbiting the sun, it'll gradually move across the night sky, and by carefully measuring the positions of these bodies, then you can determine the orbit, and then we can relate that orbit through something known as Kepler's laws to determine the distance.
Excellent. Yes, final question.
Okay, I was thinking about the Miller-Urey experiment, which a biologist got some kind of gas like methane just to simulate the early Earth's atmosphere, and he added some lightnings and he made some amino acids out of these. So, are there any similar things like lightnings happening on the two planets?
We don't know. Yeah, it's interesting that I showed Harold Urey's picture and then this question came up. We think that there's materials that contain carbon and nitrogen on Eris, and we at least see carbon on MakeMake. We're not sure about nitrogen yet. If there is an ocean, that's an environment where, and you have hydrothermal activity at the seafloor, that would be the kind of environment that could promote chemistry to making more complex materials like organic materials or amino acids. But there's nothing in the data that tell us that you have a soup of organic materials that might be precursors to life. I think we're suggesting the data are telling us that there's been some kind of very interesting processes happening in the interiors of these bodies. And now we're inviting other scientists who might want to go into the laboratory and perform those kinds of experiments, but adapted to these other conditions. And then we can learn about what is possible as far as further chemical evolution of carbon, nitrogen, and water in these systems.
All right, Chris, I want to thank you. We have something very unusual in New Jersey. We have a clear night.
You better get out there to your telescopes quickly then.
Thank you for a wonderful, very, very informative presentation. Thank you
That
very
was
much.
great, Chris.
Yeah, thank you all for listening,
you.
and thanks again for the invitation.
Thank you very much for coming.
All right, thank you.
Take care.
guys.
Bye
All
now.
right. Have a good night. Thank you.